My name is Mukesh Khare from IBM Research, and I'm the Vice President for Semiconductor and AI Hardware Strategy. And I also am I'm also responsible for IBM operations on this site. So welcome to Albany. And before I start, I'm going to give you a very high-level view of So this is truly an exciting time for being in the field of computing. Worldwide, just to give you a perspective, IBM Research has about 3,000 researchers worldwide. We work across 6 continents, 12 labs, and 21 locations. And the entire IBM Research organization has essentially focusing on one purpose: to redefine future of computing. And I'll talk about how we are thinking about it, how we are putting our energy behind this initiative, and how all of the effort that this team is putting together in the space of AI hardware is coming together from an IBM Research point of view. Before I start, I would like to welcome again all of you, and I'm going to ask a question. How many of you have been in Albany site before today? This is the first time for you. Or how many of you are here for the first time? For the first time. Look at that. Did you know that this site existed? And did you know how much capability that this site has? I would really encourage you to take a visit. I think we're going to organize some tours for the site where you can see the type of capability that exists on this site. And in my view, in our view, this is, if you go look at this site, this is truly world's most advanced or very advanced site for semiconductor research in a collaborative manner. You will see so many partners here. Pretty much most of the semiconductor industry ecosystem is here. And we are all very excited and working with New York State to really build the future of semiconductor technology and AI hardware technology. So I really welcome you all. Take a look at the capability we have and how we can help, we can participate, and we can help you all to be part of this journey in this new space that we're trying to define. Some of the accomplishment, I think, as you know, IBM Research has been around for a long time, starting with the creation of Fortran, going all the way to copper technology to venturing in the space of quantum computers. And I'm very proud of the fact that I'm representing IBM Research here with a very distinguished researcher who are working very hard, essentially to redefine our future on where we are heading as an industry. And at IBM Research, we cover a very, very broad spectrum of areas of expertise. As you can see, most of the thing that touches I'll say all aspect of defining future of computing. So clearly, artificial intelligence is the number one, or right in the beginning, as we are focusing the big worldwide IBM Research energy in this direction. So I'm going to start with 3 beautiful ideas, the way we call it. And when I was listening to the panel earlier today, I felt similar ideas. And we'll provide IBM's point of view, because IBM Research is focusing on, as we're defining future of computing, our job is we are industrial research. How can we help grow IBM's and help towards IBM's business? And how do we see from an IBM point of view computing is getting redefined? We call it 3 pieces: bits, neurons, and qubits. These are the 3 pillars of computing that will essentially redefine where we as an industry are going or will go. And I'll walk you through our thought process with a little bit more elaboration on the neuron aspect, or you can call it the AI hardware aspect, which is what this wonderful conference is about and is here today. To start with, just to make sure that we cover all aspects of computing, we have been writing on this today's traditional computers, HPC, the bit idea of computing, which is essentially mathematics plus information. And this is the foundational pillar of computing that continues to be the dominant computing paradigm that we are still riding on. And as we all know, this computing started a long time back. The famous Moore's law. We all are fortunate that we are able to ride the Moore's law and truly enjoy both the scientific breakthrough as well as economic benefit of Moore's law, which essentially is a economics law. How are you going to make more money every 2 years, essentially, by innovating in the space of semiconductor technology? And later on, from IBM, as you all know, Bob Dennard created the fundamentals of scaling theory, how you are going to go on this journey of Moore's law. So clearly, this is just to set the stage as I'm building, clarifying or communicating how we see the future of computing. And so that is the train that is going on, that has significant investment. And as you will come and visit this site, we are very excited that we are part of that journey, and we are continuing to drive the frontiers in the traditional computing space. Now let's go to the next part, which is where this team is here and very excited about, that the next exponential is starting. Next exponential we call the next beautiful idea is around neuron, where we're combining the inspiration from biology and essentially working on building AI systems. That we call as the second pillar of computing. And you have seen some of these pictures. This idea and some of the things we heard earlier on has been around for a long time. As you know, in early 1900s, Santiago Ramon Cajal, he essentially was you can call it the father of neuroscience. He was the first one who essentially started to look at the microstructure of brain and start to map it. And humans start to get inspiration from very, very early work to start creating artificial neural network and back propagation. And some of these ideas that we are working on right now has been around. A lot of these have been around for a while. The mathematics have been around, especially in the space of neural network. And obviously, this conference is going much beyond that. And now we are really starting to make financial gains and really generate value for the industry from the fundamentals that has been around for more than a century now. So the way we see it as that a part of AI now really works, and that's why we are very excited about it in certain very specific domain, such as language translation, speech recognition, object detection. You can clearly see that the capability of these AI systems for this narrow AI using deep learning, generally speaking, is superhuman capability. Our systems now for this very narrow space can do job much better than even human can do. This is amazing. This is where things start to get very exciting. However, the way we see this is that there are three phases of our journey from where we are, which is very exciting, which is in the narrow AI space, to all the way to the end, which is still a science fiction, which you can call it a general AI, which the space where we see there will be significant value created beyond where we are in the narrow AI is what we define as the broad AI. And what is broad AI? Broad AI, where we are combining learning plus reasoning. You're looking at multitask, multi-domain, multi-model, and also learning from small set of data. And this is where you start to solve the problems which are really hard to solve, but which has significant economic and societal benefit. And that's where we are. We are in the journey. We are in the beginning of what we call the broad AI. And this is not just a great scientific project, but what we estimate this space has trillions of dollars of market opportunity. And that's why we are all here. That's why IBM is investing so heavily in this space as well. So that's our second pillar, which is the computing, which is what we call building AI systems, the way we look at it for the future of computing going forward. Now, look at it a little bit more detail. We started from the neuroscience concepts, started to create AI abstractions, started to create neural network, and then start to translate into hardware. We at IBM created some very, very early image recognition machines, and the most popular deep learning hardware today, as we all know, is GPU. Now, if I look at it, now combine the two, so the two topics that I talked about, if you start to look at it, the computing has been evolving, and the concept around AI or artificial intelligence has been evolving, and they're starting to converge. And we're starting to get the benefit of both the huge computing horsepower that is being generated through, you can call it traditional computing or through Moore's law, and a significant scientific breakthrough in understanding of how do you create the right model, the right algorithm, and how do you start to get in, create superhuman capability in certain domain of AI, and start to converge. And from IBM, we started to converge them together, and we're able to put together world's most powerful supercomputer, the Summit, which we call is what we call always, the Formula One. It tells you the capability. It's not that everyone can buy that, but it is something that tells the possibility of such things are possible for very small, maybe 2 or 3 clients in the world who can afford it. So this is the supercomputer. We built 2 of those. And right now, we are very proud that the world's #1 supercomputer and #2 supercomputer is the US supercomputer, which use technologies that we developed. And you can see some of the specs associated with this supercomputer. So let's go through now. Well, great. This is a great supercomputer. We could show what is possible. But the problem with this system is it consumes a lot of power. It consumes power of the, it uses about 13 to 14 megawatt of energy, which is just unimaginable. You can essentially power a village just for running one computer. And you can look at it, right now, the narrow AI can do a good job, but it consumes a lot of power. A lot of power. We showed some of the results where for some of these, imaginative type of data set training, we could do that using 4 GPUs. It costs, 385 kilowatt and takes 16 days. We could do distributed deep learning, and that can accelerate the speed at which you can do this training. You can do it in 7 hours, but it costs 450 kilowatt. Clearly, this is not sustainable model. This is great. This is great to get things started, but the expectation or the challenge in front of all of us here in this community is to figure out how do we go from here, where you're essentially consuming energy of 1 or 2 homes to generate to train these models, to actually being able to go do these things, which can be done in minutes or in seconds with energy that is much more reasonable. In fact, there is an estimate that if we continue on the journey and the rate at which the demand for some of these AI application is going, that the compute energy consumption could be more than the total energy generated on Earth by 2040. And that's just not a sustainable model. Something has to change. And that's why we are all here, to essentially go figure out, hey, what's next? We believe in collaboration. And one of the things that we from IBM launched as a partnership model earlier this year, what we call AI Hardware Center. It's a very ambitious collaboration with a lot of partners here in semiconductor space or in the AI space, a different aspect of our technology, where we are bringing together, because we really believe that AI has moved from a phase where it was a concept, it was an algorithm, it was software, to the fact that it's hardware. It's hardware, and that's where we have to really invest, and that's where I was trying to build the case that the rate at which the way hardware is going is just not sustainable. It will stop. And we are very excited about this journey. Here, what we're doing is bringing the true expertise from industry in this collaborative ecosystem in a partnership mode so that we can really generate the hardware that can sustain or that can provide the right content for a long term for AI systems. So where we are today, great. We have GPU. They are defining, what are possible with the type of workload and the type of data set we've got. Now here is where we see the roadmap from IBM research as to the journey that we want to go on to redefine the future of computing in the AI space. And it's great that the performance has been improving in the digital space well. However, what we want to do is to continue on this journey. We believe that if we are focused, we are innovating in the space of both architecture, device, and algorithm together, we could continue this path of approximately 2.5x improvement in compute efficiency per year for at least one more decade. And that's the journey we are on. And that's the journey that we are trying to drive with our partners in the collaborative ecosystem I talked about on this site, working with our partners and working with our sites across the world. And I'll describe some of these things in detail. We start with our digital journey because that's a technology we already have. Then we start to move on what we call analog AI core, where using some of the non-volatile memory elements, yes, they are not ideal. I completely agree with that. I don't like it too. But that's what we've got. And let's start to use what we have before we start to make the ideal device. At the same time, I'm very proud that this community in this space, working in this collaborative manner, has the talent to essentially come up with these new materials that can essentially follow the type of questions that were being asked by the panel. Can we have a symmetric property? Can we have I heard even billions of states. I'm trying to get to like 100 state that can be stored in these devices. So we want to go on this journey where we can continue to maintain at least a 2.5x improvement per year in compute efficiency going forward in this space of AI hardware. And some of the things that we're talking about, going beyond digital, going into looking at non-Weinman architecture, and I'll describe this a little bit more subsequently. So the way we are thinking about it is that in order for us to build a broad ecosystem in the hardware space, we want to focus on the smallest possible unit, which we call a core. So we're going to focus on cores. And then IBM can definitely use it for our own purpose in the systems, in the data center. And of course, some of our partners can use it for their own applications, whether it's edge or whatever devices that they are building. So they can use the core as we are innovating it together in this, space and customize it for the type of application that they're trying to drive, the type of power envelope that they're trying to work within. And looking at all aspects, whether it's inference, low power, or they're constrained around die size, cost, etc. But clearly, this way we can bring the industry together to essentially create this roadmap or the future for AI hardware. A little bit more what we have done so far and some of the success that we have had in this space, starting with digital, and the fact that there is significant progress made in the space of low precision or reduced precision computation, where we are essentially trading the precision for compute efficiency and then focusing on algorithmic improvement for accuracy. And we are starting to reduce the number of bits that we can use for precision in the digital space first. And here what it shows is how we have been on this journey to understand the fundamentals of how we can go both for training as well as for inference, start to reduce the number of bits for this computation. And some of the early work that we did for reduced precision was in 2015. We started to use going from 32 to 16-bit for training and 8-bit for inference. And we are on this journey. We are, as you can see, we continue to publish. We saw some of the very exciting results or very interesting work from startup earlier on. This is one of the things I wanted to talk about is that startup and hardware was like no relationship between semiconductor hardware and startup if you had looked at like 5-6 years ago. And now there's like a complete renaissance going on where so many startups are coming up with great ideas in the space of AI hardware. And this is wonderful. This is the type of excitement that you want where VCs are actually investing money in hardware technology when everybody was trying to take money out of it. This is like nobody wanted to touch hardware. It's too expensive and very, very high risk. But this is the time. This is the time when these ideas are coming out and startups are excited, the universities and students and the entire community is excited to go on a journey which is doable. Start to build some, unique SoCs for certain type of application, starting with our view is that, hey, going in the journey of reduced precision. We have extended this journey all the way to, we presented in last year 8-bit training and 4-bit inference. We are now going towards 2-bit inference, and we are building those chips. And some of these chips are already built. We have probably will have those for display in this conference, so you can go see, touch, and feel, and see how those chips are performing. And in this space of approximate computing, and in general in the space of AI hardware, you have to look at it comprehensively. Right now, we are in the space where you cannot just focus on optimizing hardware. That is not enough. And that's the value that we bring to the table. Fortunately, with IBM Research, we can bring expertise, whether it's in the architecture space, programming model space, or algorithm and application space, because you have to look at it end to end. And you can't optimize one without other if you're trying to look for building the really fully optimized system for AI right now. And these are some of our results where we were able to show that 8-bit precision results, which are essentially comparable to some of the 32-bit baseline work. And we are continuing to go on this journey and continuing to present both hardware results as well as simulation results out of many sites from IBM Research right now. So that's about digital. You have to start with digital. You have to start innovating on what you've got. And then start to innovate new materials and new devices into the next space, which is what we call is analog AI core. Let's go leverage our material science and our device technology and start to create new device for this space. And clearly, some of the things that we had talked about earlier on, yes, we have to start eliminating the one Nyman bottleneck where you're moving data between memory and compute all the time. We are starting to map, and these are not new concepts. We're starting to map these neural networks into the cross-point array and starting to use some of the non-volatile memory elements as to store weight. And you have seen IBM's work in this space. Clearly, we are starting to focus and optimize the NVM around phase change memory material. Phase change memory material is not, we're modifying that stack to essentially focus on going out of the memory space to go in the space of what is required for essentially AI applications for deep learning right now. And you will see some of the presentations on how we are starting to what we call projected PCM, where how we are starting to optimize it so that it can start to, yes, it's not ideal, but how we can use it to start to get better than where digital is in the analog AI space. And then we go all the way to what is the optimized material, where you can have essentially a symmetric property, conductivity going across both directions. Clearly, today, we are not ideal. We start to fall off. However, this is where we are starting to leverage our our competency working with our ecosystem partners who have tremendous expertise on this site in the space of material science and developing new materials using today's equipment or modifying today's equipment to build this new material system, where you can really get the ideal properties that you're looking for let's say the ideal synaptic weight, which is symmetric and can store multiple states. Our target is at least to be able to store 100, if not billions. Maybe someday we may go there as well. And we are using some of the known materials like hafnium oxide, because these materials we need to be able to integrate that with our conventional fab. And they can be exotic, but if they're exotic, then we need to figure out how we're going to introduce that in the fab, because the infrastructure which has in our industry has already invested billions and billions of dollars, and we'll try to figure out, hey, how we use that as we are going in this journey of creating new devices for essentially representing these AI systems. So this is the second part of our view of the second pillar of this fabric that we are putting together as we are defining the future of computing. Now, looking at it even beyond that, some of the work that Winfried is doing, looking at it not just the machine learning but machine intelligence, how far we can go which is like truly inspired by biological systems, not just emulating on what can be done with today's computer, looking at truly a biological and neural model, context-aware learning. You will also see IBM's neural computer that Winfried has brought here. Some of the work that we're doing is very far out, looking at it, hey, what we can do today and how we can extend the state of the art from where we are for deep learning and machine learning to go all the way towards the machine intelligence and starting to think. And this conference is, of course, very interested in that space. And we are very happy that we have a team which is looking at that space as well, as we are starting to find the application for the near term. Third axis, which we also want to add as we are defining the fabric of future of computing, is the quantum computing. Quantum computing is as fundamental as the other two forms of computing. And this is the third beautiful idea we call the qubit idea, which is essentially we are using the physics and the nature and combining it with information to build quantum systems. Now, I'm sure all of you have studied fundamentals of quantum mechanics in your colleges. Clearly, you go from 2 bits to now you go to a qubit, which is essentially not as defined, and you have both properties associated with the qubit, which is both superposition and entanglement, and you're trying to figure out those fundamental properties of superposition, entanglement, and inference to how do you build your quantum system and essentially define or go figure out how, for certain class of application, how this can be far more superior compared to the classical system or even AI system. And the advantage of working with the quantum system is that it gives you an exponential benefit if you compare the quantum qubit versus the classical bit. And you start to get into a regime where the certain type of problem that you can solve with quantum computers can just never be solved by any computer ever built on the planet. So you're starting to get into a regime which is really exciting and truly far-reaching from where we can imagine right now. And this concept, the quantum concept, has also been around for a while. And this was a very famous conference that was held at MIT, where the whole idea that Richard Feynman's idea that, hey, you know what? If you really want to work and simulate nature, then you have to use the properties of nature. And nature is not classical. Nature is quantum. So if you want to really, really represent and build natural system, then it has to be a quantum system. And clearly, that was a beautiful idea. There's a lot of theory that went into building and thinking about quantum system. And now we are here. We are here when quantum computer is reality. It's not a science fiction. And I will show some of the results that we are putting together, some of the systems that we are building as a third and a very important pillar of future of computing. So this is when the theory came out, or when a lot of scientists like yourself got excited about, hey, this is how we're going to simulate nature. To going into building, starting to build, starting to do research. This is some of the research that we are doing, or we have been doing in our, our space in Yorktown Heights, and starting to build the real quantum system where we know how to control the system, how to cool it, how to make sure that the results that you're generating out of these quantum systems are going to be useful for real life. And this year we announced IBM's first IBM Q system, which is a system, which is a real commercial system. And if you get to visit Yorktown Heights, you can go and use this system or see this system. And these systems are available. And we have 5 quantum computers which are available on cloud, which every one of you can use for free and start to play. We are building ecosystem around it. It's the ecosystem to be able to program this quantum computer, to be able to write codes, to be able to play with it. And there is a kit that we have put together. It's called QuizKit that you can download and start to learn and start to build expertise around it and to be able to exploit this system as well. And just for like a very high level introduction, you always start with the digital system. You start to send your data, what you want to compute. However, it goes to electronics and essentially gets converted from digital to microwaves, and then it goes and starts to go inside the cryo state. And on the quantum chip or quantum processor, that's where it starts to compute, which is at 15 millikelvin, and you go back through the electronics, through the microwave signal, back through the digital form and back to your computer. Essentially, what you're doing is using digital computer to control the electronics and converting those algorithms or the compute that you want to do, send it through the electronics, convert it into microwave signals, and perform your compute at a very low temperature, and then send it back. So that you can understand on the classical side as well. The way we see it is that, hey, there's another exponential that is starting. And what we see is that, okay, in 1965, Moore's law was presented as like, hey, next exponential. Clearly, we are enjoying that. We are still riding that journey. But what we are seeing is there's another law in the space of quantum computing. We call that Gambatta's law. And who is Gambetta? Gambetta is the leading researcher at IBM who is driving the space of quantum computing. And essentially, it looks similar. It looks like we are at the beginning of this journey around quantum computing, which will take us through another, as you can see, a long exponential as we are redefining the future of computing as a society, as the leadership in this space. And there is a certain class of problem that can only be solved in the quantum space. The problems that we are looking at, the problems associated with chemistry, material science, machine learning optimization. These are the type of problems that we are working with, and we have put together an ecosystem of partners who are also helping us figure out what problems are worth solving, how those problems can be solved better than the classical computer. And there is a certain class of problem that we are very excited that will truly show superior results or superior efficiency as compared to what can be done with the classical computer. So here comes the 3 pieces or the 3 pillars of future of computing. The way we see this is you will continue to have classical computer. That will exist. And they will solve a class of problem that we need them for. There are AI system, which is the biologically inspired system, and the quantum system. And looking at it from an IBM's lens, which is more of an enterprise company, it is essentially a heterogeneous computational fabric. All of them will exist together. And the way we see it is that a hybrid cloud is the mechanism for consuming these for enterprise. Of course, there's a big space in the edge, and that's a huge market. But the way we look at it is, hey, all these 3 systems will evolve, will develop, and will put together a secure heterogeneous fabric so that depending on the type of application, the type of workload, and the type of customer that you are working with, like banks that somebody said earlier on, where you cannot, or oil and gas company or the airlines, which is what we go and work with. Clearly, we'll put together this fabric or heterogeneous fabric so that we can optimize for the type of application or the feature that we are looking at. And then you start to grow, because now that's the core, that's the nucleus. You got to have the real technology at the beginning. Then you can start to put more content on it, such as intelligent automation or application, because now more people can log into and use this hybrid cloud with the secure heterogeneous fabric of 3 pillars of computing, which is really foundational to which the way we see the future of computing is going to evolve. And now we will start to see significant impact to the society and to the community as a whole. Before I go, I come back to AI, because this is a conference which is more neuro-inspired, more focused on AI. And yes, there is we at IBM wants to be very we want to be very clear on how we are developing these technologies. So in order for us to be very transparent and be very public about it, we made very public our principles on what are we going to follow as principle as we are developing these AI technologies. So number one, the purpose for the AI technology that we are developing is to augment and not replace human intelligence. That's very important, because there is this worry, the concept that, hey, I don't know where this thing is going. Clearly, that's number one. Number two, we want to make sure that there is trust and transparency on how we are developing, deploying this system and handling data. And as you can see, there's a lot of concern about it in the society, in the industry, but we want to be very clear that this is our principle. You need to have your true north. You need to know where you can always calibrate, and if you're off, you can go back. We want to make sure that the system we are developing or the technology we are developing is non-biased, it's inclusive, it's using the data that is really representing the type of problem that you're solving. So clearly, that is the second part. And the third part, which is very equally important, is skills, that we want to make sure that not only we develop technology, but we also help build the skills in this area so that people are trained and they can contribute and be part of creation of AI system or the technology in this space. So I wanted to close with or almost close with the point that, yes, we need to make sure that IBM as a company has very clearly identified we're going to follow these guiding principles as we are working and going in this journey along with all of you. So with that, I'm very happy that the NICE conference is here, and these are some of the talks that IBM team will have, as you can look at it, as well as the demos that we have put together. And I'm very happy and proud that we are able to host this wonderful NICE conference on this site and enjoy your activities here. Thank you.
Thank you, Mukesh. So we have time available for a few questions, if you'd like.
Thanks. I just first wanted to say thank you. I really enjoyed learning about your vision for the future of computing and how neurons and bits and qubits all relate. So that was really enjoyable.
Thank you.
So my question is specifically about the AI course that you guys are developing. Is any of that information available publicly to sort of learn more about how you define, describe, and detail these cores?
Yes, some of it is available public, and I guess through the demos, we will clarify that. We've been publishing it on a regular basis. We have, we have two core family. One was completed last year. We have completed core family 2, and we plan to have one family of core per year. That's our journey, as I was talking about, 2.5x per year. So, you can either contact me or you can talk to folks in the demo, and they can provide you more information, which is available in the public domain right now. Okay.
Let's go ahead and take Mukesh again.
Thank you.